Okay, so you should watch this video after you have tried to uh, do this problem by yourself. Okay, so this is my solution. Okay, we load the dataset first, and as you can see, there are some numerical columns and some categorical columns. Okay, we want to keep all of them. So at first, we want to keep all the categorical features and apply the label encoder. So we are going to throw the column we are going to predict and two numerical features. And after that, we want to create the default dictionary, so we keep a record of how the categorical columns are converted into numerical columns. So this is the converted numerical columns. And after that, I want to add the numerical features back. So I put two numerical features back. And after that, this frame contains all the numerical features. Okay, and after that, remember we have a new entry we want to predict. So we have to make a new data frame only for that entry. And after that, we have to follow what we have done before. So for all the categorical features, we want to apply the same label encoders to custom into numerical features and numerical columns. And then for the two numerical features, they are temperature num and humidity num. I just keep them as is. And after that, I need to put together the converted numerical columns and the two originally numerical columns, and then I have the new data frame to be like this. And after that, I train my model and then predict the new entry, and I got a yes. So this is the process on how we can make use of naive Bayes to do a prediction. And there's one thing we want to pay attention to. So here, if you take a look on this data frame, you may find the ranges of those a total of six columns. The ranges are not the same. However, I didn't really do a standardization, right? So I didn't apply a standard scalar here. So why? Why it is not necessary? So think about that. The reason is, in this case, we are not paying attention to the distances of the samples. So remember, when we need to do the standard scalar, the reason is when we are measuring the distances between two samples, we don't want one feature to dominate the distance only because that feature has a bigger range than another feature, right? So we need to do the standard scalar only when we are dealing with the distances between samples. However, in this case, we don't have to do that. In the naive Bayes, we are doing the prediction based on the prior probability and the posterior probabilities. So we are not measuring the distances of the samples. Okay. So here is a quick wrap up. So for the naive Bayes, the cool features are, one, naive Bayes has very low computation costs. So if you have a big data set, and usually naive Bayes should be one of the doable algorithms. And another thing is, well, even though just now we did the prediction based on yes or no, well, it can also work on the predictions with multiple labels. And the last thing is, well, it can be used in the text analytics problems. So we can use the naive Bayes to do text classifications if we want to. And the problems. So the biggest problem of the naive Bayes is we assume that all the features are independent. Well, and in the real world, this may not be true, and especially if we are dealing with a data frame with many features, and we can't really assume all the features are independent. So another thing is, if we have a categorical feature and it's not observed in the training set, and this is a problem. Say, for example, in the overcast, there is one possible type of overcast. It doesn't show in the training set. And our naive Bayes model doesn't really have that in its model. It's not in the label encoder, and this could be one of the problem. And for the naive Bayes, well, even though eventually we are going to predict and make the prediction based on the posterior probabilities, we don't really take the posterior probabilities like something we are going to rely on. We are going to use them for the comparisons, but we don't really use that for we take that as the real value, or we take that as an estimate of the real value. So what do I mean here? So at the very beginning, we have those two posterior probabilities, right? So given we observe the x, the probability of seeing that as a yes is 24%, and given the x, we see the no is 94%. So for those two probabilities, we don't really take them serious as the real posterior probability. However, we take those two probabilities, and then we want to do a comparison. Based on the comparison, we say given x is already there, the likelihood of seeing a no is higher. This is what we can comfortably say. However, we don't really take the 94% as a real value we are going to use. Okay, so those are the wrap up of the naive Bayes, and I will see you guys tomorrow. Bye.